Welcome everyone to the second online seminar of the ISSI-BJ on Things to Come seminar series. I am Laura and I am the PR and editorial manager of the International Space Science Institute Beijing. And I would like to welcome our honored speaker, Professor Ralph Lorenz from the Johns Hopkins University Applied Physics Laboratory. Thank you for accepting our invitation. And you can see in the webcam also our ISSI-BJ Executive Director, Professor Wing Ip. And before I actually give the floor to Professor Ip and to Professor Lorenz to actually formally start the seminar, I would like to give a very brief introduction to ISSI-BJ and to our On Things to Come seminar series for those who are not familiar with it. ISSI-BJ, the International Space Science Institute Beijing, was established in 2013 thanks to the agreement and cooperation between the International Space Science Institute in Bern, Switzerland, and the National Space Science Center of the Chinese Academy of Sciences. Since then, ISSI-BJ has organized a wide array of activities and events such as forums, workshops. We have working groups, international teams. We also have visiting scientists. And we try to be a neutral floor for the international scientific community to meet in Beijing and gather here to work on their research. Unfortunately, given the current situation, the pandemic, we were not able to organize face-to-face in-person events this year. But thanks to our new executive director, to his energetic and positive work, Professor Ip, who joined ISSI-BJ in June 2020, we have started this new seminar series. As I mentioned, it's called On Things to Come. This is the second one. This is the second lecture. And our On Things to Come seminar series focuses on ongoing and future space missions. And therefore, we have today Professor Lorenz, who will give a presentation, a lecture about NASA's Dragonfly mission. And without further ado, I would like to give the floor to our Executive Director, Professor Ip. And thank you for being here and for attending the seminar.
Yes, can you hear me?
Yes.
Yes, welcome everybody. We are very happy today. We have Dr. Ralph Lorenz giving us this talk, the second talk in this series. And Ralph is a penetrometer scientist and an engineer at the Johns Hopkins Applied Physics Lab. He has a long experience and a distinguished career in penetrometer science. And he was the engineer in charge of looking after the Huygens probe construction. And he went to Arizona as a postdoc, and then in 2006 he started working at the APL, Johns Hopkins University, until now. He's famous for his work on Titan and on many other things, and he's a terrific author. And he has written, later on he will tell you, he has written 9 books and 300 papers. And I really don't know how he does it, but then let's hear what he has to say. And now this Dragonfly mission, he is serving as the mission architect. And that must be a very interesting and glorious job. Ralph, this is all yours, please.
Okay, thank you, Wing. Let's see, Laura, how do I share? Oh, there we go.
Yeah.
Show my screen. I'll turn the video off. Well, good morning, good evening, everyone. Let's see, turning the video off just to avoid bandwidth issues, and put this on full screen. So, oops, do you see the slide properly?
Yes.
Great.
We can.
Okay. As Wing said, need to talk about Dragonfly, which is NASA's new Frontiers class mission. That's a sort of $1 billion mission class completed. So I'm talking. There are, even though we are only a year since selection in Phase B, there's now, I think, well over 200 people involved in Dragonfly, and I'm merely reporting. But I'd like also to give a little bit of the background of how we got here. Let me also mention just APL is a laboratory associated with Johns Hopkins University in Baltimore, and it's involved in many planetary missions, many Earth orbiting satellites as well. It built the original navigation satellites, the transit satellites used by the US Navy. But in the planetary mission context, probably the most relevant missions are NEAR, the first contact with an asteroid, the messenger orbiter that was at Mercury for many years, and New Horizons that flew by Pluto and Arrokoth. In the space physics domain, where we built the Van Allen probes, and the Parker Solar Probe is yielding very exciting results. And I think in just 2 or 3 years, our mission DART, dual asteroid redirect test, will be encountering energetically a near-Earth asteroid. So there's lots going on. It's a really exciting time. And see, there we go. Okay, so a little bit about me. I actually trained as an aerospace engineer, but over the years have become more of a planetary scientist, and I happily enjoy the sort of meeting ground between those disciplines. They are fundamentally different ways of thinking, and often the communication between the two tribes, if you like, is challenging. I was actually a very junior member of the Huygens project team in ISSI, but went on to build a little part of the Huygens instrumentation, as I'll describe. When I had my first postdoc in Arizona, I worked on the first maps of Titan that we made with the Hubble Space Telescope, and I was involved in planning Cassini's radar observations. And Professor Ip was probably too modest to mention his role in basically being one of the handful that originally proposed Cassini, that made Cassini happen. So we're all very grateful to him for that. Cassini, even as Cassini just arrived, there were ideas about how we might explore Titan after Cassini, and I'll talk about some of those ideas. And I was very involved in some of those. These days, I'm involved in the Akatsuki Venus Climate Orbiter, and enjoy working with my Japanese colleagues on that, and on the InSight Mars lander, which is still going strong, recording meteorological and seismological data at Mars. So I have a great job. There's a lot going on and a lot of interesting problems to work on. If you want to know more, I've written some of it down, as Wing noted. I've had the fortune to be able to enjoy writing, and have been able to crank out a few books over the years. The most recent one on the right is a big colorful volume that has all the latest Cassini mosaics and final results, and a little bit about Dragonfly. I came out in August, but I've written on a number of topics, some engineering, some about aerodynamics and space systems failures, but much about Titan, of course. So let's get to Cassini and Titan. Cassini was originally proposed in 1982, and was proposed as a joint European NASA endeavor. Originally, the concept actually was that maybe the US would provide a spare of the Galileo probe, and ESA would provide the orbiter, but in fact the roles changed over the years. One of the ways ESA works is that the member states receive contracts in the same proportion as the budget they provide to ESA. And so the project is an interesting patchwork of contributions. I like to say, if you were a project manager and you wanted the job done, you just give the whole job to Germany, and it'll be fine. It'll work great. But of course, what the project manager has to do is allocate 20% or 25% of the contracts to France, and 10% to Italy, and 2% to Belgium. And so it's a very interesting sort of jigsaw puzzle, just contractually, to say nothing of all the technical challenges. I like to point out this picture on the right, where you see a Spanish structure of the Huygens probe being attached to the French heat shield on a dolly that comes from Austria that has to fit through this door in a test chamber in Germany. And all these details, how the bolt holes line up, and the electrical connectors, and the computer signaling and handshaking, all that has to be figured out, on paper before metal is ever cut. And in fact, it's very interesting for me because I got involved in the Huygens project just at the beginning of phase B, the detailed design phase, which is exactly where Dragonfly is right now. And you can sort of see a lot of the same thought processes and formulation exercises going on, and equipment being shuffled around to fit in the best places and so on. Cassini was an epic endeavor. Development started in 1990. We got to the launch pad in 1997. We launched a couple of weeks late due to a problem on the pad. It took us 7 years to get to the Saturnian system, making 2 Venus flybys, 1 Earth flyby, and a Jupiter flyby on the way. Cassini and Huygens orbited Saturn together for about 5 or 6 months, and then the Huygens probe was released and descended on Titan for 2.5 hours on the 14th of January 2005. It survived landing. We didn't necessarily expect it would survive landing because we had no idea what the surface would be, and in fact, it operated until its batteries expired. But that really paved the way for future exploration in that it kind of showed Titan as a real place. And then Cassini continued to explore the Saturnian system and I think Titan from orbit for what turned out to be the next 12 or 13 years. The nominal mission was only 4 years, but the resources were very carefully husbanded, and the spacecraft was built with great attention to reliability, and indeed it worked very well right until the end in September of 2017. My own little bit of the Huygens probe, 14 grams of it, was a sensor called a penetrometer. There's a little disc, if you look on the lower right, there's a little white disc of a piezoelectric ceramic that generates a voltage when it's squeezed. And this was mounted to the bottom of the Huygens probe. And there was no guarantee of getting any data at all from this. Of course, if the probe didn't survive landing, then we wouldn't get any data from this. But by being mounted on the bottom of the probe, and the probe fell under its parachute at 5 meters a second, then this instrument was rammed into the ground and generates a force profile. And there's some laboratory test results from my thesis on the right. Dry sand. When you push your finger into dry sand, you can feel the grains locking together, and so you get this sort of smooth ramp of increasing force with time. Wet clay has a more or less constant resistance, like a plastic or a viscous fluid, and gravel has these spiky signatures with this amplitude and spacing of the spikes relating to the particle size. And so, I spent 3 years as a graduate student, designing and building and testing this, and then it went into a cabinet and was eventually integrated with the rest of the instrument, and then the instrument was integrated onto the probe, and the probe was integrated onto Cassini, and Cassini was integrated onto the rocket. And then we waited 7 years. And of course, when we got the data, and this is me at the European Space Operations Center in Darmstadt at the Huygens encounter, the data we got on the left was of course nothing like anything in the lab tests, and that's kind of the way it should be, right? It's fun to have a new puzzle. But when we sort of looked closely at it, and we hadn't seen the pictures from Huygens at this point, those were being looked at by another instrument team, and in fact in another building in the first few hours. So we just had to sort of decode this, and if you ignore the big spike and this sort of bump, then basically it's flat, a bit like the wet clay. This bump was just kind of the hilt to the back end of the sensor hitting the ground. The spike we couldn't interpret unambiguously. You know, was this like a spark that jumped between the probe and the ground at contact, or did we hit a pebble, or was there some sort of crust? And actually, one of the ideas that we just kind of playfully floated was maybe the surface is like creme brulee, you know, like a crust over some sort of soft mud. And the media loved that. In fact, there were, I remember, about 80 of us scientists at the European Space Operations Center, and there were about 150 journalists. I mean, it was a quiet news week, and this was a very exciting event to cover. Anyway, the principal investigator of the surface science package instrument of which this sensor was a part, John Zarnecki, who's also very involved in ISSI, hesitantly offered this analog at the press conference, and the media were very pleased. The headline in Nature magazine was "Titan team gets just desserts with creme brulee surface." One other thing I like to point out, being from Scotland, is this number at the bottom of the plot, the mission time. This 8869.76 seconds is the interval between the time that the mortar that deployed the parachute was fired until the buffer containing this impact signature was frozen by the signal crossing a threshold. And that time depends on the drag coefficient of the parachute and the density of the atmosphere, and whether we landed on the top of a hill or at the bottom of a valley. You know, all these uncertainties that went into the planning of the descent duration. And in fact, we had a sweepstake, a bet running on exactly how long this time would be. And in fact, John Zarnecki won the sweepstake, the prize for which was this bottle of 16-year-old Lagavulin single malt whiskey. So it was a good end to a long day to share that with colleagues. So Titan became more thuygens just a dot in the sky. It became a place. And this is a mosaic put together by Eric Karkoschka of the Huygens images taken during descent. They were kind of a jigsaw puzzle because, in fact, the probe did not spin as expected. And so the images were acquired at more or less random azimuths and had to be stitched together. But what we saw was, a bright highland dissected with river networks with little valleys that looked, for all the world, just like river valleys on Earth. The probe landed in this dark foreground terrain, which we interpret to be a sort of a broad stream bed. There's evidence of liquid flow in the past. The ground was actually damp. We know that there were volatiles sweated out of the ground by the probe's heat. Basically, it was damp with methane. So sometime in the not too distant past, there had been rainfall here. The observations that Cassini has made over the years show that probably there's a storm at any given spot, maybe once a century, maybe more frequently than that, once a Titan year. But you have an interesting juxtaposition here that the ground was damp in the foreground here, but off in the distance you can see these two little streaks. These are actually shallow sand dunes. The sand is dark. So we have a world here on Titan where the materials are different. This is ice and organic matter, made by the photochemistry in the atmosphere. And the temperature is 94 Kelvin, the gravity is 1/7 of Earth. You know, all the parameters are different, and yet the landforms that result are very similar. So there's a lot of interesting comparative planetology and geomorphology and meteorology that merits Titan as a body of comparison. We knew already from Voyager and from ground-based spectroscopy the basics of radiative transfer in Titan's atmosphere. Basically, the haze is thick because the atmosphere is thick. The atmosphere isn't actually that hazy. In meteorological terms or aviation terms, the visibility is well over 20 kilometers. It's just that because Titan's atmosphere is so vertically extended, we look through a long column of this light haze, and so the atmosphere is more or less opaque to visible wavelengths. As you go towards the near infrared, it gets progressively clearer, and we were able to make the first maps with Hubble, and then Cassini obviously did much mapping with its camera. But there are wavelengths where methane absorbs light strongly that form these deep bands. And it was these bands through which Titan's atmosphere was discovered by Gerard Kuiper in 1944. And these have to be taken into account. For example, Dragonfly will use a LiDAR instrument to assess the terrain for safe landing. And obviously the wavelength that that LiDAR operates must not be in one of these methane bands. Because we're 10 AU from the sun, there's 100 times less sunlight falling on the top of the atmosphere, and only about 1/10 of that gets through the haze. So it's like a heavy overcast on Earth. So it's 1,000 times less bright than noon on Earth, but that's still 1,000 times brighter than full moonlight on the Earth. So you know there's plenty of light. You would see perfectly well. But one does have to pay attention to the optical design of cameras, especially on a moving platform, because the exposure time on a moving platform is limited to avoid a motion blur, for example. So, you know, Huygens and Cassini gave us a lot of the environmental parameters with which to design a future mission. One thing that people often ask about is methane rainstorms. The seasonal pattern of weather on Titan follows the sun. Titan's axis is tilted, much like the Earth, so Titan has seasons. And when Huygens arrived in 2005, it was late southern summer. The sun was down at minus 25 degrees latitude, and there were clouds and presumably storms around the South Pole. And that's where we would expect them to be one Titan year from Huygens' arrival, which is 2034, which is when Dragonfly is planned to arrive. There are storms at low latitudes. We saw them with Cassini. In fact, we even saw ground on Titan's surface that was mid-gray at one time, and there were clouds nearby. And then the ground darkened after the clouds disappeared, and then progressively brightened again. So we interpret this as evidence of rainfall darkening the surface, and then the rain progressively drying out over the next few months. So we know the hydrological cycle on Titan is active today, but it is confined in latitude and season. So at low latitudes, which is in fact where Dragonfly is destined to go, the storms will not appear until the equinox season, or around about 2040. There are some points in aviation one is obliged to pay attention to. For example, icing. Ice that forms on lifting surfaces can disrupt the airflow and degrade the performance. But that should only happen for methane at relatively high altitudes, above about 14 kilometers. And part of the story there is that actually the nitrogen in Titan's atmosphere dissolves in methane and lowers the freezing point, you actually have to take the binary thermodynamics into account. And this is quite well known from the liquefied natural gas industry. And the plan is that the Dragonfly will make profiling flights to measure the structure of the boundary layer up to about 4 kilometers, but that's well below the altitude at which icing might occur. Let me just check briefly that the audio is working okay. One kind of does this open loop, but just to check.
Yes, I can hear you properly. Yeah, it's working.
Okay, thank you. Wind, of course, is important for any kind of flying vehicle. It's also important for vehicles on the ground. For example, if you're doing seismic measurements, the wind background is very important, and so understanding the characteristics of the boundary layer turbulence is important. We have the Doppler tracking information from Huygens that's shown at the right. There's a little bit of wind shear. And if you compare with terrestrial aviation, at one point during the descent, there is what would be called light turbulence in terrestrial aviation. Really, Titan's atmosphere is actually quite quiescent, as you might expect, being so massive and so far from the sun. And in fact, with global circulation models that we've tuned to Titan's parameters, we can replicate the large-scale patterns that we see. For example, the rain over the polar summer and the equatorial spring. We can replicate the pattern, the orientation and shape of the sand dunes. So we are getting progressively more and more confident in how good our models are of Titan, which is of course reassuring in terms of planning a mission. Probably the strongest winds we could expect are those generated essentially by dust devils, by dry convective vortices in the afternoon, and even those would only be 3 or 4 meters a second, and would happen maybe once or twice over a 3-year mission. It's possible to generate stronger winds in methane rainstorms, but as I said, those are not expected at the season and latitude that we're planning for. And there are now large eddy simulations coming up to speed to model turbulence on the landscape scale and model effects like the wind speeding up over a sand dune. And so we have a good modeling basis with which to design a future mission. So of course, the great challenge with a world like Titan, which is shaped by many different processes, and you can see on this near-infrared mosaic, and remember that pole-to-pole distance is 7,000 kilometers or so. The low latitudes have these dark areas that are all covered in sand dunes. The high latitudes have methane seas. There are a number of impact craters, actually relatively few. There are a couple of features that may be cryovolcanic. There are mountains. There are river channels. You're always sort of spoiled for choice, right? Where would you explore? You don't want to choose one single place. And the virtue of the Titan environment is that it allows you unprecedented mobility because of the low gravity and thick atmosphere. That you don't need to stick with just one place. You can move around over substantial different distances. And in fact, the places we think are most interesting from an astrobiological standpoint are those where Titan's abundant organics have interacted with liquid water. And liquid water, we expect at perhaps cryovolcanic features, and there's not really a strong consensus on those beyond a single example. And impact structures, impact craters, the violent energetic event causes local melting, and that exposes organics to liquid water for an extended period. And you can sort of see right in the middle of this mosaic, and there's my mouse pointer, this impact structure, SELC, 80 kilometers across, is I'm getting a warning that the connection with the server has been lost. Can you still hear me?
Yes. The connection.
If I change the slide, do you see it now? A slide with the orange Titan on it?
No. Are you
Okay,
changing
then
the?
I did. I wonder if my connection dropped.
Okay, 1 second. Next slide should be Titan offers the next step to answer fundamental questions, right?
Yes. Is that what you're seeing right now?
No. Oops. Maybe I can display the slides and
yeah.
you just tell.
Yeah, why don't we do that?
Okay, 1 second. Okay. Can you see it? Hello?
Well, sorry, I was showing my own screen. So,
yeah.
Hang on.
Can you see the slides now?
I cannot, but I'm going to assume that you're showing them okay.
Okay, I'm on Titan offers the next step to answer fundamental questions.
Okay, thank you. Sorry about this hiccup. By going to an impact structure, we can investigate just how complicated the chemistry on Titan has got. When you add water to Titan organics in the laboratory, you very quickly make amino acids, the building blocks of proteins. You make the number of bases, pyrimidines, that encode information in DNA, but we don't know how far the sort of self-assembly of these building blocks might have gone. These transient liquid water environments on Titan, like impact melt sheets, would last for tens of thousands of years. There are of course many aspects of Titan to understand. Its deep interior, for example, that probably has a global liquid water ocean, perhaps under 100 kilometers of ice crust. And there's the meteorology, of course, the methane weather. So there are many things to explore about Titan. In fact, one single mission, even a mobile one, can only answer them in part. But we think we've got the most important. So if we go to the next slide, it should be ideas 1990s to 2004.
Mm-hmm.
In fact, many of these questions and the wish to answer them were known well before Cassini arrived, and there were ideas about how to explore Titan kicked around even then. Many exploit Titan's thick atmosphere. So one idea was that you could use Titan's atmosphere to slow down an orbiter, to error brake, or rather error capture into orbit. So you can see this sort of big dish orbiter packaged inside an error shell, a heat shield. The thick atmosphere, of course, appeals to ideas of hot air ballooning, and there were ideas for airships and hot air balloons, which would be a great way to survey large areas of the surface from a few kilometers altitude, to give you that sort of airplane window view that Huygens showed at one spot. But balloons are actually a challenging platform from which to try and access the surface material. Measuring the composition of stuff on the surface is what would be of perhaps most scientific interest. So next slide, ideas 2008. Yep. Well, my computer is actually locked up. There were after the first few years of Cassini results, there were studies set up in NASA. I chaired one of them about what would we like to do if there were no constraints, even if you could have as big a mission as you could wish for. And we said, well, an orbiter with 2 landers and 2 balloons would be great. And that got kind of pushed down to an orbiter and a balloon and a lander. An orbiter gives you the global context, lets you see seasonal variations and map the planetary body as a whole. A balloon would give you that sort of airplane window regional view over a diverse range of terrains. But to access the surface material, measure the composition of stuff on the surface, you'd want a lander. And you'd also want to do things like seismology to investigate the interior. So these 3 different platforms access different scales of phenomena and address different science objectives. And it was actually quite interesting when I was challenged as to, okay, so you've got three elements, an orbiter, a lander, and a balloon. Well, what if you could only have 2? Which would you pick? And it was quite clear when you look at the traceability matrix, what science gets done by which platform. And the answer was the lander. You get much more important science out of the lander. And even though the balloon is sexier, it's actually less vital from answering big questions. And that was actually quite an unpopular answer, but it's what the numbers said. Next slide. In 2009, there were some initiatives to explore less ambitious missions at Titan, in particular those that might be enabled by a radioisotope power system called the ASRG, the Stirling generator. One was a capsule to float in one of Titan's seas called the Titan Mare Explorer mission. And that was actually selected for a Phase A study. We got several $1 million from NASA, and we did things like testing sonars in liquid nitrogen and modeling the motion of the capsule in the waves. It was quite a detailed enterprise, but in the end, NASA selected InSight instead. There was also an idea for an aeroplane on Titan, one that wouldn't ever touch the ground. It would just fly continuously, like a sort of long endurance drone. And again, that would give you the airplane window view, literally. But next slide. Actually, the thing that gives you the biggest bang for the buck is something like a helicopter. And in fact, this was recognized even around 2000. That if you want to explore different parts of a planetary surface, or if you're deploying troops or rescuing people from unprepared locations, a helicopter is the ideal platform. And in fact, the low gravity and the dense atmosphere both work in your favor. And the helicopter should, in principle, work. But helicopters are sort of complicated mechanically. Not really appealing from a spacecraft engineering standpoint. And the challenges of autonomy were also significant 20 years ago. But now there's been the drone revolution. There's lots of autopilots and sensors that allow you to fly without a person in the loop. Another enabling technology, next slide, should be power, is the multi-mission radioisotope thermoelectric generator. This is the plutonium-fueled thermoelectric device that can operate in planetary atmospheres, unlike the RTGs on Cassini or Ulysses, for example. And this sort of power source is very important for Titan in particular, not just because it gives you continuous electrical power day and night, but also because it produces a lot of heat. In orbit, that's almost a waste product, but in Titan's dense cold atmosphere, it's very important. We actually pull that heat in with a fluid loop to keep the inside warm. I actually had the opportunity. My last business trip in the COVID world was to the Idaho National Labs to make some measurements on the RTG that's now on its way to Mars on Perseverance, and the plan is subject to government approval the Dragonfly would use a similar unit. Now, 70 watts or 100 watts of electrical power, next slide, is not enough to fly. You need several kilowatts to fly a vehicle on Titan, even with the low gravity and thick atmosphere. So what we do is over the Titan night, remember Titan's day is 16 Earth days long. So you have basically a week when platform on Titan's surface at low latitudes is on the far side of Titan. It's in darkness and it can't see the Earth. So during that time, we just do monitoring measurements, meteorology and seismology, and the battery, a big battery, is progressively charged up. That's the blue curve, especially at the right. And then when the sun comes up, we assess the weather, check whether it's safe to fly, and we fly for only half an hour or so. Although we can cover many kilometers in that time. And over the course of a Titan day, after we've landed at the new site, we'll send data back to Earth, and that's the sort of sawtooth drops in the battery state of charge there. So maybe we have 4 or half a dozen contacts with the Earth during the Titan day, and then we go back to sleep and recharge the battery to do it all again. Probably would fly only once every 2 Titan days or TSOLs. The second day at a given landing site would be devoted to sampling surface material and analyzing it and sending the data back. And the energy that we didn't use for flying during that sol would allow more downlink, more data to be sent. The next slide is the Dragonfly vehicle. So it's ugly from an aeronautical standpoint. Remember, it has to fit inside a heat shield for arrival at Titan. It comes down by parachute until the last couple of kilometers, and then it flies under the power of 8 rotors. You can see the principal investigator, Elizabeth Turtle at APL, with the rotor blades. The rotor blades are actually about the same size as the ones on the Mars helicopter that is on its way to Mars right now. But that's only a 2-kilogram vehicle, whereas a Dragonfly is more like a 3/4 of a ton. It's the same size, but a little lighter than the Curiosity rover. I mean, it's a big vehicle. We communicate to Earth with a circular high gain antenna that's folded flat onto the lander deck for flight. We can use that same gimbal mechanism to pan around a couple of cameras to make panoramas. We have forward and downward looking cameras for imaging during flight, and sampling drills. We'll come back to those in a moment. Next slide. Right, so Dragonfly was originally conceived in 2016. Was proposed and selected from a pool of about a dozen ideas for comet missions, Venus missions, but in the end there was a phase A study of Dragonfly and of a comet sample return mission, Caesar, and NASA selected bravely Dragonfly last year. Because of NASA budget constraints in fiscal 21, in part due to the impact of COVID, we've now been asked to plan for a launch in 2027. It remains to be seen whether we can maintain our 2034 arrival date. That depends on the launch vehicle that is chosen by NASA for us. I think I've described some of the operations already, but importantly, there are some great visuals, some really neat videos at our website. You can see the URL there. So let's leave that up for a second. And I think we're probably getting tight on time, so I'll need to run through the next slides fairly quickly. So next slide is flight on Titan. Is that what you're showing, Laura? Like terrestrial helicopters, there's an optimum flight speed where the power that's used is actually a minimum. And for a Dragonfly, that's about 10 meters a second. So if you multiply half an hour by 10 meters a second, you get that we can fly 20, 30 kilometers. Probably will typically fly less than that. And in fact, our forward progress will be a third of that. So maybe 6 or 7 kilometers at a time. The reason for that is at the bottom, what we do after the first landing, which must be done by the vehicle itself, is the team on the ground can look at all the images and so on taken by the vehicle from the air and look at promising new locations. And what we do after we've identified where to send the vehicle is basically tell it to fly out to a prospective unscouted new location, C. And then it would come back to A. Sorry, it would fly out to B, come back to A, because we know A is safe. Then if we like what we see at B, then we'll plan to go there next. But we'd fly out from A, go over to C, check it out, and then land at B, because we've checked that out already. And so we do this sort of 2 steps forward, 1 step back leapfrog approach to basically ensure we never have to land at a site we haven't assessed, to our satisfaction on the ground. All the vehicle has to do for itself is fly to waypoints that are designated by us on the ground, and it has to use a LiDAR system to avoid rocks. Right? If we know there's a broad area that's mostly okay, and there's 1 or 2 gullies or rocks, then it will avoid those hazards. But the high level assessment of where is scientifically interesting, that we do on the ground. So the instruments we carry, the key one, next slide, is a mass spectrometer. Melissa Trainer at Goddard Space Flight Center leads that. It has many features of the instruments on their way to Mars and on Mars right now, on Curiosity and ExoMars. It's a mass spectrometer with 3 front ends, laser desorption, pyrolysis, and derivatization. So now if you go to the next slide, it can look at for the quite complex organics that we expect to find in abundance on Titan. Looking for organics on Mars is like looking for a needle in a haystack, but Titan is awash with organics, so that the challenge is sifting them all out. The derivatization little chemistry step in our sampling system lets us look at the chirality of amino acids, whether they're left or right-handed isomers, because chirality is considered a possible biomarker. But whether there's, however far prebiotic chemistry has gone on Titan, we'll also be able to diagnose some of the chemical processes that happen in the atmosphere that form the haze. Next slide. So the drill system that acquires our samples is interesting. We have 2, 1 on each skid, and the drill makes cuttings, and these cuttings are sucked up by a vacuum system, actually, like a vacuum cleaner. If you go to the next slide, there's a URL. If you search YouTube for Draco or Dragonfly Drill, you can see this in operation. This is a mock-up, the Iron Bird, that was built for the Phase A study with full-size prototype components of the drill and pneumatic transfer system and the sample carousel and the blowers. And we operated this at cryogenic temperatures, and we drilled solid ice at 90 Kelvin. We drilled ammonia-rich ice. We drilled basalt. We used oily sand as a sticky simulant for Titan. We used very fine-grained powders to assess electrostatic sticking. We challenged the system in a lot of ways, and it's a very flexible means of obtaining surface material and transporting it to an instrument. The next slide shows close-ups of some of the parts. We have a conical drill, so that it won't get stuck. and it makes these cuttings, and the cuttings are sucked up by the sort of scoop-shaped inlet at the right. The material as it flows through the pipes is captured by these little cups with a sort of angled deflector, and then those cups are transferred into the instrument for laser desorption or pyrolysis. It's really a really innovative and novel system that was a lot of fun to work on. The next slide describes a Gammaray spectrometer, and that's actually built at APL using some of the heritage for the instruments on MMX and Psyche. Normally, planetary missions exploit cosmic rays to excite gamma rays from crustal material, and by capturing the gamma rays at different energies, you can identify the surface elements. Because Titan's atmosphere is so thick, the cosmic rays don't really get down to the surface, so we have to bring our own neutron generator, pulse generator, a bit like on Curiosity. But this will let us interrogate the surface elemental composition within about an hour of operation without doing any sampling. So just after we land, we can zap the ground and assess whether it's ice-rich material or it's carbon-rich, or just get that sort of crude overall classification. Next slide, we have a suite of cameras, as you might expect, and that will expose the Titan surface material to us at a range of scales, from the landscape and the aerial scale down to the microscopic. We have a sort of zoom camera, a bit like the hand lens imager on Curiosity, that can resolve individual sand grains. The next slide shows some neat tricks we can do at Titan. You know, the illumination is sort of a dull red, but by using colored LED illuminators, we can sort of explore the composition at the grain scale, and you can see some laboratory samples of tholin and ice illuminated with some specific near-infrared wavelengths that highlight some of the differences. Many organics, polycyclic aromatic hydrocarbons in particular, fluoresce. So at night, we can use an ultraviolet LED to excite fluorescence of the surface material. That will be a really neat experiment, I think. The instrument that I lead, the next slide, the Dragonfly Geophysics and Meteorology package, or Dragnet, is a sort of combination of MET package and seismometer and some sensors on the skids. We use wind sensors derived from those flown on Beagle and Schiaparelli. We record pressure, temperature, methane humidity, hydrogen abundance. So these will give us a handle on Titan's meteorological variations and whether, for example, methane is coming out from the interior. You know, are there sources or vents? Next slide is also the Dragonfly Geophysics and Meteorology package. It's showing some simulations by Simon Stahler of earthquakes on Titan, and in particular the reverberation timescale of P waves will give a more or less direct measurement of the thickness of the ice crust. And we actually are getting a very sensitive seismometer from JAXA, one that was designed for the Lunar A project many years ago. But that will work very well at Titan's low temperatures. And in fact, our colleagues at JAXA did some low temperature tests a couple of years ago that show the instrument works at 94 Kelvin very well, which you know, one can imagine better seismometers, but it's difficult to get very sensitive instrumentation that will work at these very low temperatures. So better wrap up. The next slide, mission timeline. This slide has been somewhat overtaken by events, in that we currently are assessing the trajectory options associated with the 2027 launch, but our intent is very much to arrive at the same season as Huygens to exploit that atmospheric similarity. It will take us about 2 hours to descend by parachute after entry, and then we drop away from the parachute and fly and land under rotor power for that first landing. The next slide shows some detail near the impact crater Selk. You can sort of see the crater just at the top left, but in the middle are these kind of tapering parallel dark lines. These are, and there's a terrestrial example in radar shown at the right. These are tapering sort of shallow sand dunes. The area between is largely sand covered. So we're very confident about finding some safe places to land. The next slide shows a wider mosaic showing the crater itself, and some composition interpretation from Cassini VIMS data, near-infrared spectral data. And the blue material we believe is water rich, so it's material thrown out by the crater during the impact cratering event. So this water rich material that was probably heated will be what we're most interested in exploring. So we'll land in the dunes to be safe, and then progressively march in 5 kilometer, 7 kilometer hops towards the crater. So I better end there. The last slide reminds you of the website. There's a lot of resources there, and we are just in the beginning of development, and many years to go. So I look forward to seeing how this develops, and invite you to follow us along. So thank you.
Thank you very much. Professor Ip?
Yes. Right. Raf, can you show yourself? I don't know whether he has the connection.
Professor Lorenz? Are you there?
Yes. I don't see the chat because
Okay.
I'm not sure that it's refreshing.
Okay.
Maybe you could choose 1 or 2 questions and read them for me.
Yeah. So you can't see the chat. Yeah, immediately. So we received 1 question from Professor Michel Blanc. He says, many thanks for a great talk. I have a question about Titan and habitability. It is often said that the first condition that defines a habitable world is the presence of liquid water. In the case of Titan, we know there is now a subsurface ocean, but it is needed to assume that this subsurface water reservoir has a connection to the surface and its rich family of organic components to consider that Titan is habitable. Is there any evidence of this connection between surface and subsurface ocean? And if so, will Dragonfly be able to find evidence for it?
That's a big and interesting question, of course. Thank you, Michelle. So there's no direct evidence of exchange of material from the deep interior, from the ocean to the surface. There is one feature, Doom Mons, which has been interpreted to be a cryovolcano, but that doesn't mean the material came from the ocean. It would have to ascend through 100 kilometers of ice to get to the surface, and there's not an obvious mechanism to go back down from there. The impact melt that we will explore with Dragonfly is presumably derived from the near surface, so it's not ocean material necessarily. But we are making our first mission after Huygens. This is still very much a reconnaissance. We would hope to understand the ice thickness from Dragonfly's seismic measurements, and combined with the inorganic composition, the salts that are in the ice, those will help us understand the evolution of Titan and the likely characteristics of the internal ocean. But we won't be accessing ocean material directly, we think.
Okay, thank you very much. We also have another question sent by Professor James McCavitt. Thank you for the great presentation. Does the navigation and takeoff landing software have roots in other autonomous surface spacecraft, or has this been developed from scratch given the unique conditions on Titan, atmospheric disturbances, etc.?
Very good. So in fact, a lot of the guidance, navigation and control aspects of Dragonfly are derived from a lot of development work that was done on lunar landers in the late 2000s and early 2010s at APL and by NASA. So obviously the control laws, the actuators, the fact that we're using rotors instead of rocket motors are different, but the underlying logic is the same. Autonomous image processing, deriving velocity information from successive image comparisons. A lot of that is derived from effectively spacecraft autonomy. But we are working with colleagues at Penn State University. There's a NASA Center of Excellence in rotorcraft technology there. So obviously all the control system logic has to be informed by the aerodynamic performance of the rotors. And when you have an octocopter, some of the aerodynamics are actually quite complex. The lower rotors at the back are sometimes in the downwash from the forward rotors when we're in forward flight, and that needs to be taken into account in the autopilot. We were lucky actually to get special permission during COVID to do some rotor thrust testing in one of NASA's wind tunnels at NASA Langley just a few weeks ago. So there's some special flavors to this vehicle, of course, but the guidance, navigation, and control, some of the autopilot stuff is actually derived from lunar lander work.
Thank you very much. And then we have two similar questions submitted by Professor Luisa Lara. Are the flights going to be affected by winds? How do you plan to solve the issues wind might arise?
So I didn't dwell on the numbers, but the slide on the Huygens measurements of wind in the lower atmosphere show that the winds there are 1 or 2 meters per second typically, and our optimum flight speed is 10 meters a second. So yes, we may encounter headwinds or tailwinds as you do on Earth, and those have to be taken into account in the energy estimation for a flight. But they are something like a 10% effect, so it's just a factor in the planning. There's no particular challenge.
Thank you very much. We have then a question submitted by Professor Leonid Gurvitz, who says, power for data downlink is obviously an issue. What ground-based resources are envisioned to get those precious bits from Titan? Nominal, TSN, anything else?
Hi, Leonid. Nice to hear from you. Leonid did a great experiment tracking Huygens with VLBI. The framework of a competed mission is such that one is obliged to propose using standard deep space network assets. We use an X-band coherent link, but in principle there is no technical reason other assets such as the radio telescopes couldn't be used. Leonid's very, very astute in pointing out the acute value of data from Titan. We can achieve 1 or 2 kilobits a second downlink. So we will get far fewer pictures than you're used to getting from Mars, for example, where there are orbiter relay assets in place. So we have to choose the information very carefully. We can do things like send down thumbnail images, highly compressed data products, and from those identify the images with the most valuable scientific content. We'll obviously use data compression to the extent we can, And it's entirely possible that if other ground-based assets are available to us, that we might use them. But that's an agency decision. That's not for the implementing organization to decide.
Thank you very much. Then a question by Professor Cianucci. Is it more complex to run such a mission from a planetary protection of view? Does NASA set some solid rules for missions to such planets with probable lives?
Yeah, planetary protection is an important consideration. In fact, we are working with the NASA Planetary Protection Office to identify our requirements. There is a preliminary categorization of Titan missions, including Dragonfly, which is Category 2 star. That is missions to targets that are of interest for the origin of life, but where there is no life expected to be present in the surface environment, nor is terrestrial life brought on the vehicle expected to flourish. Right? The surface is at 94 Kelvin. Nothing can grow at these temperatures. So our expectation is that we will remain in that category. So there's no sterilization required, nor was there for Huygens, for example. It may be that we are asked to inventory the bioload on the vehicle, to identify what organisms are present on the vehicle. But the expectation is that it's essentially that documentation exercise. Titan is just too cold for terrestrial biology to flourish.
Thank you very much. Professor François Roland says, thank you so much, Ralph, for this very nice presentation. Some of the complex organics to be analyzed on Titan's surface may be very sticky and difficult to sample and transfer to the chemical analyzer of Dragonfly. How do you plan to solve this problem?
Yeah, that's an excellent question. Thanks, François. So as I said, during the development of our drill system, we use things like sand mixed with oil to see, just how sticky a material we could handle. The way to view this is not, could the aeroplane crash? Because if you ask the binary question, can you imagine a material that will be sticky? The answer is, of course, yes. You cannot be sure that there won't be a sticky material. So the challenge is one more like, managing your cholesterol, right? You know that sticky material may accumulate to some degree in the pipework, and you make it a consumable to be managed, a budget to be tracked. We have sensors on the skids that can estimate whether the ground is damp from its thermal behavior. We'll look with cameras to see if the ground is glistening, whether the light reflects as if the grains are wet. So we will have an assessment of what we think the quality of the material is before we commit to ingesting it. We can poke the surface with the drill and see whether the walls of the hole are smooth, or whether the particles kind of avalanche like dry sand. So we will have a good sense of what we think the mechanical properties of the surface material are before we commit to ingesting it, and we'll obviously make that decision whether or not to ingest or from which skid to ingest very carefully at each location. If we don't like what we see, we don't need to take a sample. We can just wait and move to somewhere where the material looks safer.
Perfect. Thank you very much. I think this was our last question. I think no one else has submitted any further question. I don't know if Professor Ip maybe has some questions. Professor Ip?
Yeah, maybe let me ask the last question. What is the chance of having a rainstorm on Titan?
So as I mentioned, rain is a conditional phenomenon. I mean, overall, a single spot on Titan probably sees rain only, once a Titan year, maybe once a century. But we know already from EMs and from the telescopic observations that the rain tends to occur during polar summer and equatorial equinox. And so since Dragonfly will be landing at low northern latitudes during southern summer, the rain is in another place. It's like saying why don't penguins get eaten by polar bears? It's because they're just in different places.
Okay.
That said, we will design Dragonfly to be tolerant of being rained upon. From a thermal perspective, there's some enhanced cooling, but the probability of our flying, for 1/2 an hour every month, at the same time that a methane rainstorm that we didn't know was there appearing is very small. So we're confident that we don't have an unacceptable hazard.
Okay, very good. You have thought of everything. Ralph, thank you so much for this excellent and interesting talk. And I would like to shake your hand at that time. So we'll wait the next time.
Too.
Yeah, thank you so much.
Well, thank you. Sorry for the AV problem.
Bye-bye.
Thank you very much. No problem.
Right.
Thank you,
Good evening.
everyone,
Bye.
for joining the seminar. Good evening. Bye-bye.